G'day, welcome back to another episode of Big Cube, the series where we're trying to make 1,4-dicarboxyl cubane from household materials, and we're trying to make a lot of it. Made the cube before, didn't make very much of it, now we're trying to make a whole heap of it, so that everyone in the world gets a little bit of cube. That's not what we're trying to do, but we're trying to make a lot of it anyway. Last episode, we successfully completed the second step and made the ketal, this molecule here, and we have it in this container here. Look, this is our ketal. So that means today we have the bromination step, step 3. Last time we ran this bromination step, it worked somewhat well, I would say, somewhat well. We got reasonable yields, probably not great yields, but it did work first time. However, the key thing is last time we ran this bromination, it was really the first time where it kind of scaled down a lot. We made a reasonable amount of ketal in the small scale synthesis, 40 grams or something like that. But by the time we did step 3, this bromination step, we only had a couple grams of the tribromide, so this tribromo species, which is what we need to make here. Obviously, if we're trying to make 100 grams of cubane, which is our plan, we need a lot more than a couple grams of tribromo ketal here. I have some numbers somewhere of what we need to do. Okay, I've got this scrap of paper, but this is the biggest scale I think we can manage. I have some new 2-litre flasks, so we're going to be running this in a 2-litre flask. Are you ready? This is all the stuff we need. We need 130 mils of the ketal, which we've made previously. We need 110 grams of 1,4-dioxane, which we make from ethylene glycol. We will need to make that. We need 800 mils of DCM and 167 mils, which is 520 grams of bromine. Altogether, it's 1.2 litres or something like that, but given the density of dichloromethane and bromine, it's a big mass of product. But if we pull this off at this scale, we'll have a lot of tribromo. But pulling it off is not particularly easy. There are several issues here. How do we get enough of all these chemicals? Well, there's a good and bad thing about this list. Let's start with the good one. The good one is we made enough ketal, really, in the last step, but pretty much using it all up in this reaction, which might come back to haunt me. We're going to use it all up, and that will be 130 grams of ketal. No worries. So we can strike that off the list. We've already got that. The dioxane, we'll come back to the dioxane because the bad news really is the bromine. It's a lot of bromine. This amount of bromine is not easy to make or handle, but I'm actually going to do something a bit weird in this intro here. I'm going to break tensors because I've actually done this step already. Oh, where is it? I should really put gloves on for this. Let me put gloves on. Look at this fucked bottle of bromine. It is terrible quality, but there is more than 300 mils of bromine in here, which is over a kilo of bromine. So this is enough to run this reaction. It's actually enough to probably run this reaction twice. This would have been pretty hard, pretty unsafe, and also kind of really boring to make all of this on my own. But luckily, I had some help from fellow chemistry YouTuber, Mr. Green, if you could believe that.
We are going to be making a ton of bromine. Up to a litre, we hope. That's our goal.
If we do it good. Which maybe. We're 50-50. Yeah. First time. Have you ever made bromine before?
I've made it before, just not this much.
Yeah, not in such a professional setting as this one.
Yeah.
What could go wrong? I will ask, but that I'm going to say it's a rhetorical question because there's multiple things that can go wrong.
Yeah.
So as much as we are going big scale, we're going to have to really do it.
Ice will solve everything.
Yeah, and we got to not drop the bromine, drop a whole litre of bromine on the concrete at any point. We've got to avoid that. So Mr. Green came over and we started making this bromine with the goal of making 1 litre of bromine in a day. So that's nearly 3.5 kilos of bromine. And for that, we needed to convert, over 5 kilos of sodium bromide. It was a bit of a task, I got to say. We spent all day distilling bromine, first in the 1 litre flasks and doing it on a sort of a smaller scale, though still in a 1 litre flask. And then we moved up to the 2 litre flask. What is this? Why are you shaped like that? I don't know. And we were running a 2-litre flask at the same time as a 1-litre flask to try and produce enough bromine and get up to the 1-litre mark within the day. And we were a bit rushed for time because this bromine stuff doesn't really want to be rushed. It's also quite unsafe, so we had to take our time with it. Now, we used a bit of a strange method to make the bromine. You can make bromine a variety of ways. Previously, I've made bromine using peroxide as the oxidizer, so you've got a bromide, salt, and acid, and hydrogen peroxide. People have used potassium permanganate. You can use a lot of other things. But in this case, we wanted to use calcium hypochlorite. This is a strange choice because generally people avoid chlorine-based oxidizers because you can make this interhalogen compound BRCl. So it's one bromine and one chlorine. And that is pretty much a gas. And you'll lose some yields to that. And you also contaminate your N-bromine with this bromine-chlorine molecule. However, you've got to remember we weren't prioritizing yield or purity in a sense. We were aiming for that 1 litre. So what we were actually prioritizing was speed, ease of doing it, and also cost. Because you can buy a lot of calcium hypochlorite for very cheap. So we optimized for speed and cost rather than yield, which looking back, maybe we shouldn't have done because we didn't end up reaching that 1 litre mark. And I think that was in part because of so much BRCl that was produced. It generally produced when there wasn't very good stirring, but when we were working in these 2-litre flasks with, you know, a kilo or more of reagents, the stirring wasn't very good. So
It's weirdly not bubbling up. Oh yeah, because it's got the sodium bromide.
it's kind of caking up on the top there.
I'm worried it's just going to go...
Yeah, you're right. I didn't expect it to cake so hard.
Yeah, because we left it for
Caked up.
half an hour.
It's caked up. But still let us make more than 600 mils in a day of bromine. The obvious question, of course, is why? I've got a reason for making bromine, but why did we try and make a whole litre of it? What was Mr. Green's motive? Well, I mean, you might guess that he just wanted to make a very big bromine volcano reacting with the aluminium. He'll make a video up on his channel about making this big bromine vortex, but I got to keep any leftover bromine. Watch it, the glass might shatter. So to loop back, the reason that this looks so fucked is because I poured back a lot of the bromine that we had reacted with the aluminium. It had got hot. It's got dissolved aluminium bromides in it. But it was all this bromine. I wasn't going to let all this bromine just evaporate off. I need it for the chemistry, so I saved it.
It might spark a bit.
Oh, stop! Sorry, my pouring skills aren't. But in doing so, it's pretty contaminated. So we will just have to redistill it. If we add some sodium bromide in there, I think it should cause any BRCl in there to just form Br2. So we should be able to clean up this bromine. Importantly, there's enough of it. The bromine goes on the pile with the key towel. And I will mention, I just have the dichloromethane lying around. I have about 800 mils of dichloromethane lying around. I used to get it from Paint Stripper. That was how I got it over the counter. I bought 2 litres from a chemistry supplier a little while ago. It's a little bit of cheating, but I do have the dichloromethane. So this leaves us with only one chemical left, and then we can do the bromination reaction and finally make a lot of tribromo, keep moving along this Big Cubane synthesis. So let's do some chemistry. All right, here is some ethylene glycol and sulfuric acid heating up. It's just gone this weird piss color, as things always tend to do. It was this, you know, dyed green color. I'm just using the ethylene glycol straight with some sulfuric acid. And this is the dioxane forming reaction that I've never really quite gotten a hold of, and I've done it quite a few times, so it's a little bit embarrassing. Maybe not embarrassing, frustrating is maybe the word, that I haven't been able to really master it. This is Extractions&Ire, so I very rarely master anything. Put on some stirring. The point is, this reaction kind of gets out of control for me. It looks, I mean, piss coloured now, but it will go all tarry, and at some point that tar will foam, and quite a few times when I've run this foam kind of blows through the system and ends up in your beaker. And yeah, I've got footage of that happening quite a few times. This does seem like a problem with this reaction. The sulfuric acid and the ethylene glycol eventually break down to just form long polymerous tarry carbony masses. It's a reasonably common home chemistry reaction to do because you get 1,4-dioxane, which is reasonably useful out of something that's very, very commonly available and cheap, which is this car coolant ethylene glycol. So, right, you've got these ethylene glycol molecules, and you need to get two of them to kiss. You know what I mean? You get two of them to kiss, and it releases some water. Right, this is weirdly getting erotic already. And once we've connected two together, we've got to do that again, but this time, because these ethylene glycols are already attached, it's easy for it to close in on itself. So actually, the really smart way, and a few people suggested this, the really smart way of running this reaction is to not start with ethylene glycol, but to start with diethylene glycol, and then all you have to do is kind of close these two in together. The problem is getting diethylene glycol is a lot harder. It does appear in some products, but I wasn't able to find any around the place. Ooh, we're getting some tar. I don't know where that was from. Interesting. Anyway, some other people think that running a lot less sulfuric acid throughout the reaction really reduces the tar, and it kind of makes sense. So this is 200 grams of ethylene glycol plus 20 grams of sulfuric acid, so not super high, but reasonably high. And then what I'm going to do once it's hot, which is just about now, it's starting to get even more piss colored and starting to just start to boil, I'm going to dump in another 200 mils or 200 grams of ethylene glycol. And then as we're running this reaction, I'll just keep dropping in more ethylene glycol so we don't boil it down and start really increasing that concentration of sulfuric acid, because I think that's what happens most of the time as well. As we're distilling off the ethylene glycol as dioxane, the sulfuric acid concentration is increasing, and then it kind of reaches a point where instead of just linking two of them together, it links them in long chains or just dehydrates them all together. You know, it's just pulling off waters randomly from ethylene glycol and forming carbon and tar. So that's what we're going to try and do. I'm going to have to do it immediately and stop yapping because this is getting hot and this stuff isn't even connected. So enough yapping, let's mix some more chemicals up. Alright, I've been at this all day and it's kind of sucked, but I won't get up here and complain. We've gone through the whole bottle, really, of this, which is fantastic. I really actually, on my scales, only weighed out to be 940 grams, which is well short of a litre, but it's probably actually on my scales for being out, although that is out by a long way. Anyway, I'm collecting a little bit more piss, still got that to add. It is getting tarry. I caved and added a bit more sulfuric acid because it's just too slow. Yes, it's less tarry if we really reduce the sulfuric acid level, but it is a lot slower. So really, you can add heaps of sulfuric acid and just do it fast and loose, and then you have to baby it along to make sure it doesn't foam over and ruin everything. Or you can add in a little bit less, and you know, it takes longer, but you don't have to monitor it as much. So I don't know which one's better. I've been here quite a bit, just watching the sun move across the room. So like, whatever. Not complaining. Yeah, we'll end up with quite a bit of liquid. The next step is to put in quite a bit of sodium hydroxide, which will separate the dioxane and the water, and also polymerize a lot of impurities that are in there, like acetaldehyde, which is quite prevalent in this as well. Great. Okay, that's it. That's the whole update. Thank you. Thanks for tuning in. All right, this is our tar that we have that contains our dioxane. It's not meant to look this bad. I just got it wrong slightly, this procedure. You do add sodium hydroxide into the dioxane to make all these impurities tar out and separate the dioxane and the water. But really in the procedure, you run another distillation first before adding the sodium hydroxide to remove most of the impurities before doing this sodium hydroxide bit. So this is what happens when I don't triple check my my reference material and the procedure before starting and thinking I just remember everything correctly. It's fine, our dioxane should be fine, but I was a little concerned because I remember adding the hydroxide previously and it goes a little red or something like that, but it's never gone this like black color. But that's usually because we throw away most of the acetaldehyde, which is a byproduct of this. We throw that away in a distillation first before adding the hydroxides. I don't know, the dioxane should be fine, so we're just going to distill it straight out of here. It's going to distill over as the water azeotrope. I am worried that our yields will be very low because of the small amount of sulfuric acid we used. I don't think, now that I've done it, it worked very well just because it didn't produce the dioxane at really a high rate. So I'm worried that we distilled over a lot of the ethylene glycol. So a lot of this volume of liquid is water and ethylene glycol and not a heap of dioxane, which would really suck. But I suppose we'll find out. I won't get all doom and gloom ahead of myself here, but that's something I'm worried about. Could all be fine. It could all be fine, you know? Anyway, let's get this set up. I'm just going to reuse a lot of these parts in this distillation setup, because why not? The distillation slowed down and it looks like we've just hit 100 degrees, so the temperature was at about 85 and then it stopped and then the temperature went up again. So that's it for our dioxane. Surprisingly early. Well, maybe not surprisingly, but definitely disappointingly early. There's a lot more liquid in that flask, but it looks like we've distilled all the dioxane and water azeotrope out. So this is roughly 70% dioxane. We tried to convert a whole litre of ethylene glycol. It should be alright, it should be enough for what we need. Maybe, just enough, but yeah, this method I tried to do to improve yields has absolutely cooked the yields. We're only like 2 or 3 videos into this series, and I've already generated several monumental tars. I mean, look at this, look how thick this sludge is. I gotta clean all this shit, and I'm ignoring it because I don't want to. Ooh, 134 grams of water and dioxane azeotrope. Not only is that absolutely abysmal yields, but I don't think it's enough for what we need. Luckily, I do have water dioxane azeotrope in the cupboard. I think from the last time we did this Cubane reaction, we probably recovered some. So that should get us over the line. There is, what, approximately 60 mils in there. Alright, so we'll combine all our dioxane, water, azeotrope and add some sodium hydroxide. We want to neutralize any remaining impurities and also drag out the water until its own layer so that we can just distill over nice dioxane. Even the easy shit is hard. Alright, we have our piss in the flask here, our dioxane. It is reasonably dry. All the water has been removed. There is probably still some dissolved water. Water and dioxane have a lower boiling azeotrope, so as long as we throw away the first stuff we collect, that should have all the water in it, and then everything from then on we'll get as dry dioxane. Now, usually what people would do here is to dry the dioxane with sodium. And I wasn't going to do it. I wasn't going to do it because it's not really in the spirit of this series. We're trying to use chemicals from the hardware store, blah, blah, blah. But it is a safety reason. I'm worried about peroxides in the dioxane because there was sort of a 2-week lag between making the dioxane and running this distillation. And what happens is if there's peroxides in there which form from oxygen in the air and exposure to light and that kind of thing, they're not usually that dangerous, but as we concentrate it down, the peroxides can concentrate and then explode at the end. I have a little bit of sodium, and the sodium should destroy the peroxides, and then I'll just fill safer about this. Not going to compromise on safety, so we're going to put the sodium in. The sodium will react with the water and any, peroxides and stuff. I'm sure the peroxides wouldn't have formed because it's over sodium hydroxide, blah, 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 but I'm just overthinking it. But sometimes for safety, it's nice to overthink things. And I do just have lumps of sodium lying around. I mean, they're under mineral oil. They're very bad lumps. There's a big block, but these are just small offcuts. I can just cut into it. It is nice and shiny underneath, under all that crust, but the crust shouldn't matter either. Yeah, that bubbling there is any water getting destroyed, so... And that's good. Water is an enemy at the moment, so... Alright, we're just about done. I don't want to boil this to dryness because there's still lumps of sodium in there and I don't want that to catch fire with all the flammable solvent. That would be bad. This is our anhydrous dioxane. We've got a little bit more in here. And I think together we're just going to be short of our target, which is both incredibly frustrating and incredibly bad, given that we started with a litre of ethylene glycol. We also have non-anhydrous dioxane. This is stuff that came over with the water azeotrope that boiled below the pure dry dioxane. So we could dry this out and redistill. It's roughly 20% water dissolved in the dioxane. I've not nailed this synthesis at all. Really not nailed it. On a lighter note, long-time viewers know that I always like dyeing my condenser water green. I know, it's always been green. It's just always been green. I like it green, and it just looks wrong when it's not green. Yeah, I had this bucket somewhere, and I tripped over it, and it spilt everywhere, and I forgot to dye it green. It's still moldy somehow, but it's not green. Anyway, before I forget to make it not green again, importantly, I'm gonna make it green. That's obviously why this dioxane synthesis didn't work. The cooling water wasn't green enough. Obviously. Okay, it won't happen again. It won't happen again. In fact, I'll put more in. This is the real science. Why do I believe that this will make a difference? Yet, things that would actually make a difference, I'm like, nah, I can't be bothered doing that. And I wonder why things don't work so well. I'm like the least scientific-minded person ever. I'm just doing all this science based on vibes. No wonder it doesn't work so well. Holy shit. Whatever, the condenser water's green. Moving on. 91.7 grams of dioxane, which is less than 110. Which means we're going to have to scale down the overall reaction. This shouldn't be our limiting reagent. Alright, I'll stop complaining. Let's just keep moving and see if we can nail the rest of the reaction. Probably going to have to come back and do all of this anyway someday, so let's just nail this bromination reaction. Which, speaking of which, let's go check on the bromine. The next step really is to get the bromine good, because that's the last piece. So, where is our bromine? How is our bromine doing? Alright, let's check on our bromine, which has been sitting in this esky here. I think esky is an Australian word. What do other people call this? I don't know. This box to keep the cold in. In here. Importantly, the timeline in this is it's roughly 4 weeks ago I made the bromine with Mr. Green. And bromine is reasonably corrosive. In fact, extremely corrosive. And even though it's sealed in this bottle here, we're still greeted with a somewhat unpleasant smell. Not overwhelming, kind of the smell of moldy piss, but none of the top notes, all bottom notes of moldy piss, none of that ammonia sort of high-pitched smells, just the good parts of the moldy piss smell. How is that for an explanation? Bromine has corroded and stained this plastic orange. It, in the first 2 weeks, nearly completely got through one of these lids, which are actually very chemically resistant, and the bromine nearly broke through it completely in 2 weeks. So, in this one, I've put a Teflon seal between the lid and the bromine, as well as some Teflon tape, because Teflon does resist the bromine, but of course the bromine works its way around the Teflon disc anyway, it seems, and has nearly broken through the second lid in another 2 weeks. Obviously, you can get better lids for this, but it does highlight the fact how difficult this bromine is to store. It's in this esky because for the first 2 weeks or so, I was buying a new bag of ice every couple of days and keeping it cold, which does keep the vapor pressure down. Obviously, you could think I could just take this bromine out and put it in a freezer, but given the way it's destroyed all this plastic and everything, you can imagine how corrosive it would be to the freezer. Anything in the fridge and freezer would take on this sort of moldy piss smell and be generally very unhealthy to eat. One interesting thing here, it looks like the bromine sort of collected around this neck of this plastic bag here, which used to have ice in it, but actually I think there's a little tie and there's maybe some steel in it. The bromine has corroded the steel so badly that it's leaking all iron bromides in there. So there was one tiny bit of metal in this whole thing, and you can see how aggressively corroded it is in about 2 weeks. That's all the bad news. The good news is, look, hey, there's still 300 mils of bromine in here. So we have actually kept most of it. Even as difficult as it is to store, we haven't leaked out a third of our bromine or anything like that. We've kept it all in the jar. It's good to go. Well, not really, not in the slightest. We've got to do some purification. Look at that stuff all stuck to the edge of the flask. We also have to remove any water from here. So we've got to add some sulfuric acid to dry out the bromine. Make sure there's no water because it's got to be dry before we add it to our reaction. And then distill it again over some sodium bromide, which hopefully remove any chloride contaminants. I could store it in some glass. Obviously the losses are going to be higher through a stopper or something like that, or maybe a well-greased stopper was probably a nicer way of storing this, but I was worried about the lid getting shot off as the temperature got really high because it's been hitting over 40 degrees here again, so the bromine pressure builds up in a flask and the stopper shoots off, then all the bromine will just be lost and I would come back here to a very, very orange and corroded esky and be very sad about it. That didn't happen, so let's go on with processing the bromine. Hell yeah, we get to distill the bromine, which looks fantastic on video and is not particularly pleasant to be around in real life. It's only me that has to suffer through fucking actually being here, so go team, let's go. And with that, we have successfully made our bromine. I forgot to weigh the flask, so I don't actually know exactly how much is in here, but it's around 300 mils, and we only need 167. It's definitely more than enough. It looks pretty good. You can tell bromine is reasonably dry when it no longer starts sticking to the glass. You can see how it's running off that glass there. If it's really wet bromine, it kind of sticks to the glass a bit more. It's not perfect, I would say, but it's pretty good. That's fantastic. So we've actually completed the whole set. I was actually so mad at having to scale down because of the dioxane that I went back, re-separated out some of the azeotropic dioxane we had earlier. So now, can you believe it, after doing it again, we have 111.5 grams of dioxane, which is just over our required 110 grams. It's still actually the limiting reagent here because we've got more than our needed 130 mils of ketal, but it's fine. We'll do it on this scale, so we're going to use all this dioxane, pretty much most of this ketal here, half of this bromine, and I think majority of this DCM. Let's not delay any longer. We've got a long reaction to do. Let's go. Let's get this set up. Okay. 3, 2, 1, set up. Go. Ready. Wow. A perfect jump cut. Look, this is the setup, and I was going to go through and fill this all up and talk you through it, but look at that temperature gauge. Temperature is very important for this reaction. It was 39 just earlier. I know there's no solvent in there, but the room temperature is about 40 degrees, and we're going to have to churn through so much ice to cool this down, and doing temperature control, I'll stop complaining. The point is, I've just set up this entire somewhat grotesque setup, and I'm actually just not going to do the reaction today at all. So we'll come back another day when it's not fucking 40 degrees. Holy shit. Look, there's some clouds these days. It should be cooler soon. Okay, here we are. It is much cooler. I had to wait about a week for the weather to actually cool down, but the room temperature is only about 20 degrees. So here we are. Here's the actual setup. We have everything in our flask as needed. We've got about 500 mils, which is a little bit skimpy of DCM. I don't know, I'm always just a bit skimpy with solvent, but that's fine. Then we have our cyclopentanone ketal in there, as well as our dioxane. Obviously up here is our bromine. We have some argon coming through from the argon cylinder. This is probably not needed, but you know, I have this argon cylinder. It's just from the hardware store for use with welding, and that's coming through very slowly, coming through the top. The argon is coming out here and just pushing through a little bit of water, because this reaction does generate some HBr gas, which we can't just seal this up and let it get pressurized, because that would be a very bad idea. But we also want to keep this reaction dry and not let too much air get back in there, air and moisture from the air. So this argon kind of flowing through it will keep it dry. We are using DCM as a solvent, which I think will dissolve quite a bit of the HBr, so we don't expect a lot of outgassing, but this should still control it. Most other people would run this reaction with dioxane as a solvent, so you just use, say, 5 times as much dioxane, so then it's the thing that reacts as well as a solvent, but obviously you've seen how much I struggle getting dioxane, so the DCM lets us, you know, once again, skimp out on the dioxane. It's all about skimping, I suppose. It's a bit of a weird setup here. This is obviously a takeoff adapter for a distillation. Very weird for it to be used in this circumstance. I'm just using it because I can't find my Clystan adapter, so there's better adapters for this, but that's fine. This is definitely a broken bit of glassware. This is Teflon tubing. This is Teflon coming in here. Yeah, this is obviously fitting a temperature probe in there. It's currently reading at 3.9 degrees Celsius, which is great. This is on the cooling bath. Obviously, I could just use an actual thermometer and do this a little bit differently, but I like having the thing here for the camera, so it's kind of sealed with this Teflon tape, which is a bit sketchy, but anyway, and through this bit of broken glassware in here, it's fine. I've got a sort of a sick perversion to reuse broken glassware. All right, let's talk about temperature, because we're obviously doing this on a cooler day and we've got all this ice here. So what's up with temperature? This is the Navy report from 1989. Goes through this sort of big scale reactions, and it does it on a really, really large scale. Some of them, like here, it's 68 kilos of cyclopentanone, which is a huge scale, but they're trying to make it on a huge industrial scale. But they do sort of what I would say a medium run, which is about what we're running the scale on as well. So we're following mostly this paper. This paragraph is of particular importance. The analysis of the bromination was followed. At the completion of the bromine addition, the reaction was found to be 1/3 complete. The second and third bromination steps proceeded very slowly at 15 degrees C, but required 16 to 18 hours at 20 degrees C and only 2 to 3 hours at 27 degrees C, which is great because that means we don't have to be here for that long. However, it continues. When bromination reactions were heated above 30 degrees for even periods as short as 10 minutes, extensive decomposition occurred and only tars were obtained upon dehydrohalogenation, which is the next step. So, if this reaction goes above 30 degrees for even a couple of minutes, it's lost. Everything is ruined. When we were considering doing the reaction the other day and the room temperature was 39 degrees, that's very bad. So we have to have very good cooling here. I got some advice from a couple of people who ran this at large scale as well in proper laboratories, and they say stirring was very important. So we've got a bit of a weird tower here, which is a little bit unsettling. We've got high stirring, so when the bromine comes in, it should stir very well, which will help with cooling. Yeah, this temperature control is very important. How do we start it? The addition of the first mole of bromine was accompanied by a large exotherm, and it was necessary to cool the reaction mixture with ice water to maintain the temperature below 15 degrees C. So after half the bromine was added, hydrogen bromide gas was evolved at such a rate that the mixture spontaneously cooled. So we might see that. I didn't see this last time when running it, but it was on a much smaller scale, and these sort of temperature things don't scale. They go on and talk about this huge scale. We don't have to worry about it too much. It was found that 1 mole of ketal, 3 moles of bromine, and approximately 1 mole of dioxane in methylene chloride, this is DCM, gave yields comparable to those in dioxane solution. Fantastic. All right. Shall we do it? Let's do it. Hell yeah. Let's go. Alright, everything went really well. I've just cranked up the argon flow to try and purge as much of this HBr gas out of the reaction as possible. It's been stirring at 27 to 28 degrees for 2.5 hours, maybe close to 3 hours actually. We've probably completed the bromination. So, how do we get our brominated product out of there? Well, first of all, we've got to get rid of all this HBr gas. We've got to slowly add some water, and then we've got to add some sodium sulfite, which will destroy any remaining bromine, and then finally add some sodium hydroxide and sodium carbonate, which will react with any of HBr and neutralize it. So once we have that, we have the water layer and the dichloromethane layer. We'll take the dichloromethane layer out. We've got to separate it off, which is a little bit difficult because there's so much of it, and there'll be quite a lot of water as well. But once we have that by itself, without the water layer containing all the impurities, we can gently distill the dichloromethane off to be left with a residual oil. Should crystallize out into our tribromo product. We're distilling it once we've removed any residual bromine or hydrobromic acid. It shouldn't really be an issue with heating it to 40 degrees, even though we've just spent the last couple of hours really balancing this bloody hot plate to make sure it doesn't go over 30 degrees. So hopefully, yeah, just running a normal distillation is fine for it. I'm going to try crystallizing it out using some seed crystals from this old tribromo ketal we made last time we did the synthesis. There's not very much in there, but we should only need a couple of milligrams, a couple of seed crystals. Hopefully trigger it to crystallize out. Yeah, it's fucking doing it. Let's fucking go. After a month of work, we're left with 170.8 grams of this dense powder that kind of has an off-putting smell of sickly, mouldy carpet. But not a trace of the colour yellow in here. This is fantastic. Not even a recrystallization needed. It looks perfect.